Hello, everybody. My name is Rohan, and I'm so excited to be part of World Coma Day 2025. I'm excited for the talks, the discussions, and truly all the enthusiasm that researchers, physicians, providers, students, patients, their family members have for advancing care for patients in comas. In this video, I'm going to try and take a few minutes to try and break down and demystify artificial intelligence, one of the emerging new technologies that has the potential to make a huge difference in helping us predict outcomes better, in helping us find better treatments for these patients, and it is going to have transformative effects in research. Despite the fact that it's so ubiquitous now in our lingo, everybody talks about AI. Still, many people don't have a grasp of some of the fundamental concepts that go into AI and how to look at AI with a critical lens. And in this video, I'm hoping to go over some of the core concepts of AI. I'm not going to go into very specific studies or specific kinds of data, but I'm going to talk about AI in general, talk about the core concepts being used, things like machine learning, deep learning, and what those things mean and how to interpret the research in the field. So I'm hoping you're going to join me on this exciting journey. Okay. Also, throughout this talk, you're going to see me morph into little shapes. Please forgive me. I did my best with this new tool. So let's start from the right from the beginning. We're going to talk about a patient who comes into the ICU with a brain injury and a comatose state. It's an emergency. The ICU team, providers, the nurses, everybody is working super hard to stabilize this kind of patient. In the process, we put in tubes, we put in lines, things that allow us to stabilize the patient's vital signs, allow them to get the medications that they need. But in the same time, all of these sensors, all of these tools are collecting massive amounts of data. This data includes things like the neurological exams that we're doing at the bedside. We're doing that in serial fashion over the course of the patient's hospitalization. We do CT scans and MRI scans to understand what's happening with the structure of the brain. We do EEGs, which are looking at the electrical activity of the brain. We're doing vital sign monitoring, heart rate, blood pressure, oxygen monitors. All of these things are continuously being collected and analyzed. Ventilators are connected to breathing tubes and they generate their own data. And there are other specialized devices like ICP monitors or multimodal monitors or NIRS devices, all of which are looking at interesting physiological data that we're also continuously recording and collecting. And all of this information is being used by the medical team to try and make important decisions. What does this mean? Do I need to act? Do I need to give certain medications? Does the patient need surgery? Does the patient need a change in the dynamic? Does the data tell me that the patient's going to have a poor prognosis or are they going to make it out of this coma? These are questions that the medical team is asking, but also what researchers are asking. How can we do these things better? Now, with all of this information, of course, your medical teams are trained to glean the most important information that they can to make decisions. But truly, given the density and the breadth of data that we're collecting, there are potentially a lot of hidden insights to this data. And using computers and especially artificial intelligence to analyze this data is going to, we hope, yield crucial insights and crucial new technologies that can help us cure coma. So before we get any further, let's first talk about what AI is, right? And how it's different from the technology that's come before. So historically, when you think about computer programming, you would sit there and you would say, okay, if I get this input, then this computer program has to process that particular input in such a way to give a predefined output. In other words, you know exactly what that program is going to do because you told it exactly what to do when it encounters a piece of information. And it's all programmed upfront. With AI, there's a fundamental difference. AI works by recognizing patterns in data, and you're not really telling it exactly what to do in the sense that you're not programming every single if then scenario, but instead you're exposing it to certain data sets. And you're exposing this program and you're letting this AI learn just like a human learns. The only difference is the computational power of an AI is pretty powerful. And so you might be able to analyze much more data than a human being can. And we're going to learn about these different types of AI technologies, things like machine learning, natural language processing, and very briefly touch on computer vision technologies. But there are actually, the AI umbrella is so broad that there may even be many, many different things that are also considered AI that we won't get a chance to talk to about in this talk. Um, so the first branch of AI that we're going to talk about is machine learning. And machine learning is one subset of AI. Instead of following fixed rules, machine learning tends to learn from experience. So essentially, you're training a computer program by exposing it to data. And how you train it can really vary, just like how you train a student may really vary. There are fundamental tasks that machine learning is trying to solve. So a machine learning program, you're giving it a bunch of data and you're trying to get it to either do a few things. You can ask it to classify the data. So once you get a piece of data, you can classify it into different categories, or you could use that data to make more of a prediction. But in both cases, you're going to train it, and we're going to talk about how that works. When you're training somebody, you have some choices to make, right? So you can train this machine learning algorithm uh, and in different ways. And there's two fundamental questions, and these two fundamental questions allow you to break down machine learning programs into different categories. The first question you're going to ask is, while training the algorithm, am I going to tell the algorithm what the specific categories they need to sort the data into are or not? And we're going to look at an example of this, but this is where there's a difference between supervised and unsupervised learning. And the second thing is, do you tell the algorithm what to pay attention to in the data, or do you just give it the data and let it figure it out? This is the difference between traditional machine learning models and deep learning models. So let's start looking at some examples. So, or actually even before that, so here are the two categories. And now let's look at an example. Okay, so let's look at supervised learning, right? In supervised learning, you have a data set, but you're specifically going to tell the computer what you're looking to classify this data into. So for example, here I have a big chunk or a big collection of little balls. Some are green, some are orange. And what I'm going to do in a supervised learning method is I'm going to pick some of these, right? And I'm going to call it my test data set. And I'm going to label these two on the right side of your screen as orange and the other two as green. And I'm going to tell it that's what I want you to do. Sort them out into orange and green. And here are some pairs which can clearly show you what you're supposed to do. And so once you train a supervised machine learning model to do that, that's exactly what it's going to do. On the flip side, there's unsupervised learning, right? So in this one, I have a bunch of data, and this is a different data set. I have some circles, some triangles, two different colors, and I'm not going to tell the algorithm what I want to sort it out into. I'm just going to let it figure out what you're going to sort it out into, and that's unsupervised learning. And so in this case, for example, the unsupervised machine learning model decided to sort it out by shape. You can imagine a scenario where it sorts it out by color or by both. And in this case, I haven't specified how I wanted to sort it. I just wanted to find patterns or groupings. That's unsupervised learning. Here's another alternative of what an unsupervised learning model could have come out with. Now, there's a difference other than supervised or unsupervised. There's also this distinction between traditional machine learning and deep learning. In other words, do you tell the program while it's being trained what to pay attention to, what features are important, right? So here we have the same data set that we had with that unsupervised training, right? But what if I said to the computer, hey, pay attention only to the shape, right? And then come up with your groups. This is what it's going to do. What if I say, don't pay attention attention to the shape, just pay attention to the color. It's going to classify the data differently. In this case, I'm defining the features that the algorithm is going to pay attention to, right? I haven't necessarily given it labels. I'm just giving it um, what features to pay attention to when you're trying to come up with categories, right? And whether those are my defined categories or the computer's decision, that's a separate question. That's supervised, unsupervised. In this case, I'm just saying pay attention to a certain part of the input. That's what a traditional machine learning algorithm does. In a deep learning algorithm, however, I'm not going to do that. I'm going to let it figure it out however it wants. So you can mix and match techniques. You could end up with a supervised traditional machine learning model. And in this case, you've clearly labeled your outcomes of interest, right? I want to sort it out into oranges and blues. And then you're telling the computer, pay attention to the color. That's a supervised traditional machine learning model. An unsupervised traditional machine learning model may be, hey, I haven't labeled them. I haven't told it this is blue and this is orange, but I am going to tell the computer, pay attention to this particular aspect of my data, right? And on the flip side there, we also have deep learning, right? So you could have supervised deep learning models. So you've labeled the outcomes of interest, but you're not telling it what features to pay attention to. It's the raw data that it just gets the data and then has to figure it out. And in an unsupervised deep learning model, it's mislabeled here on the screen. In an unsupervised deep learning model, you haven't labeled the outcomes of interest and you didn't define the features. Okay. So how does this translate into coma research, right? Ultimately, that's what we're here to talk about. We are collecting all of this incredible data. We're collecting EEGs and images and physiological data. We're giving different stimuli. We're collecting data about how the patient looks now and how they look out in the future. So we have outcomes of interest, right? We can see how people look at different points in time. We have different kinds of imaging outputs. We have different kinds of EEG outputs. We have different kinds of outcomes that we care about with these patients. And you can train algorithms using machine learning, using the data that you've collected, and you could use these different techniques. So that, in a nutshell, is how machine learning is being used in coma research. But the next question is, you're really excited about this. We all are. How do you know if you're reading a paper or you're training a model? How do you know if it's any good? Well, there's some fundamental principles that go into determining whether or not you can trust what's coming out of these models, right? So first things first, in computer science, there's an old adage, garbage in, garbage out. If you don't put in good data, or you don't clean your data properly, or don't use a representative data set, chances are your model is not going to work when you apply it in real life. So you want to make sure that the data that you're collecting and the data that you're giving to the models is good. It's appropriate if you're using labels for a supervised learning method, that those labels are done well. You want to make sure your data set is representative of your patient population. You want to make sure you're accounting for any biases in your data itself. The second thing, does the method used make sense to answer the question being asked? So in other words, if you were trying to sort it out into specific categories, did you define those categories up front? Did you do the labeling? Did you use a supervised method? That would make sense to answer a specific question. And then the third most important question actually, is once you've built this model, once you've trained a model, how are you testing it? You got to give this model brand new data and test its performance. You got to see how accurate it is in many different domains. Is it sensitive? Is it specific? What's the positive predictive value? All that basic stat stuff comes in, and you want to really understand when you're testing the model on new data, how is it performing? And then finally, are you applying it and validating it on a brand new patient data set that your model had nothing to do with to begin with? So does it apply broadly? And ultimately, you want to test these things out in real time to figure out if they work. That's where science still matters. It's not just about turning over our questions to a computer and saying, hey, fix this for us. It's about actually building these models intelligently. Okay, so you're probably wondering, hey Rohan, that all sounds wonderful. It's really cool that you're able to take these very extensive data sets and get all these new insights. Okay, so you're probably wondering, Hey Rohan, that all sounds wonderful. It's really cool that you're able to take these very extensive data sets and get all these new insights from it. That's amazing. But when I think of AI, I think of, I don't know, ChatGPT or Google Bard. So I actually have my friend here, ChatGPT, and we're going to talk a little bit about what large language models are so we can better understand them. Hey ChatGPT, this is Rohan. I'm going to talk to you a little bit about large language models. Can you tell me what those are and how they might be helpful in scientific research?
Hey Rohan, sure. Large language models, or LLMs, are advanced AI systems trained on vast amounts of text data. They're designed to understand, generate, and interact with human language. They're helpful in scientific research
Kind of,
by
yeah.
assisting with
Can you explain
literature
that to me more
reviews,
simply?
generating hypotheses, summarizing papers, and even drafting content. They can save time and provide insights by processing information faster than a human could. Does that answer your question?
Kind of, yeah. Can you explain that to me more simply?
Absolutely. Think of large language models as super smart computer programs that can read, write, and understand text. They're like having a helpful assistant who can quickly find information, summarize articles, or even help write papers. So in research, they can save you time and give you new ideas.
I'm so excited about the Curing Coma Campaign and World Coma Day, where we're going to be talking about research with regards to patients who are in comas. Can you tell me how an LLM might be useful in that context?
It can also answer questions. That's awesome, Rohan. An LLM could be super helpful for the Curing Coma campaign. It could assist by quickly summarizing existing research on comas, generating reports, or even helping draft presentations. It can also answer questions or provide references during discussions. Super handy for diving into complex topics. They can sometimes generate
Tell me, are there
incorrect
any
or biased
pitfalls or scary things that I
it's
need to be
important to
aware of when I'm
cross-check
talking
facts
about
and
LLMs and
maintain a
research?
critical eye. Also, great question. One pitfall is over-relying on LLMs without verifying their outputs. They can sometimes generate incorrect or
Thank you
biased
so much. I
information.
appreciate it.
It's important to cross-check facts and maintain a critical eye. Also, they might not fully grasp nuanced medical
That's it. That's the short primer on AI. I'm sure you're dying and itching to see the rest of the videos here for World Coma Day 2025. Just remember, there's some core principles. AI should not be a black box for you. You should be able to look at an AI paper or AI research, get excited about it, but also look at it critically, see what it's really answering, what methods they're using, and why they're using those methods. And I hope this primer will be helpful. There's so much stuff out there on AI. You're going to hear about computer vision, using video to deliver new insights about our patients. You're going to hear about foundation models, where we're building vast data set or training models, just like ChatGPT, but just on vast amounts of neurological data to ask a broader range of questions rather than just a narrow question. And then, of course, you're going to hear about digital twins. Can we use all the data we collect about a patient to create a simulated version of them and then test interventions? These sound futuristic, but these are things that are actively being researched. And I hope you're going to hear more about them today, as well as over the course of the next few years. So hope to see you around, and very excited for World Coma Day 2025.